excited to meet you all. I'm looking forward to forming more relationships with teachers in middle schools and high schools in the area. And I'm looking for partners for something that I hope to do that's related to my research. So I'm a collaborator in something called the Phoenix Collaboration that I'll be telling you about. The technical name for my field is ultra-relativistic heavy ion physics, which sounds fancy schmancy, but it's really just nuclear physics at fairly high energy. So let me, without further ado, talk a little bit about my interests. So when I give talks at these places, I often start with a pie chart like this, because this is, to me, one of the most amazing things about physics in the past half century. And that is that probably the most important discovery of the 20th century was that everything is made out of atoms. That's huge, right? Pertains to most of science. And so if you ask people, a few decades ago, what is the universe made out of? They'd say, well, it's made out of atoms, and that would have been a pretty good guess. But if you ask people today what the universe is made out of, the pie chart looks really different. So atoms, the things that we all know about, consist of about 5% of the universe, right? And then they have this dark matter stuff, and we don't know what the dark matter is. And so that's another, 25%-ish of the universe. And then there's stuff that's even more mysterious that we've only known about for 20 years or so, called dark energy. And the only thing that can make us feel good about dark matter is how little we know about dark energy. And so now we can say that as we learn more and more, we know less and less about what the universe is really made out of, what the universe is. And so everything that we can tell you all sorts of things about, atoms, constitutes only 5% of what's out there. So this is really an amazing time to be living, an amazing time to try to excite people about physics because of how much there is to explore in them. Right? Recently they've been talking about maybe modifications to our theories of gravity to account for the dark matter. That was, a few years ago, totally unacceptable to most physicists, right? So it's really an open issue as to what's going on here. Okay, so these cosmological questions are very interesting, and to sort of look at these cosmological questions again in a big context, and say, well, we want to understand the universe from its beginning to now, right? So the 13 or 14 billion years from the Big Bang to now. And most students could tell you, if you talk to them, that telescopes are kind of like time machines, right? So you point a telescope at a star that's 3 light years away, and you're looking 3 years into the past. Or you point a telescope at a galaxy that's 3 billion light years away, and you're looking 3 billion years into the past. And so the further out you look with the telescope, because of the finite speed of light, the further back in time you're looking. And so it's amazing. You just point your telescope in different directions, and you see the universe at different stages. Right? And you might think, well, that's great. So we can just use telescopes to trace back in time all the way to the Big Bang. But that doesn't work, because a few 100,000 years after the Big Bang, or the first few 100,000 years, the universe was very energetic. And there were no neutral atoms, and all the neutral atoms that we had were ionized, and so we had charged particles everywhere, and light could not travel freely through the universe, so the universe was opaque, if you go back to the first few 100,000 years of the universe. So that trick of looking back in time with telescopes, in principle, has a limit. You can't know about the universe with a normal telescope beyond a few 100,000 years after the Big Bang. So how do you then continue using something as a time machine? What becomes the scientist's time machine when the telescope trick doesn't work anymore? Right? And so when the telescope trick doesn't work anymore, you can turn to other kinds of machines. And the machine that is really great is the particle accelerator. Because when you have a particle accelerator, what you can do is you can take some matter here and some matter there, and you can collide the matter, and for a brief instant, you create the conditions of the early universe. And so then a particle accelerator, which most science students see as something abstract and hard to understand, and maybe they don't know why it should ever be funded in the first place, you can explain that the particle accelerator is a time machine in the same way a telescope is a time machine, except you can go further back in time. Right? So with a particle accelerator, the higher the energy of the collision, the more like the early universe it is, and you can probe back further and further and further in time. Right? So the machine that I work with, that I'm going to be telling you about, we can go back to the first, after the first few millionths of a second after the Big Bang, and recreate conditions in a tiny little volume of space by colliding things together. And amazing things are supposed to exist under those conditions. So I want to give you a feeling for what we're looking for. If you go back to a few millionths of a second after the Big Bang, it's so hot that no atoms have electrons around them. And the nucleus of atoms, it's so hot, 10 to the 12 Kelvin, that you don't even have atomic nuclei. There are no nuclei. In fact, it's so hot there are no nucleons, no protons or neutrons. It's too hot for those to exist. And so you melt the basic stuff that the universe is made out of, or at least 5% of it. So you melt protons and neutrons, and anyone know what's inside protons and neutrons? Quarks. Quarks and gluons, right? So you have these quarks and gluons. You melt, you have a new phase of matter, a plasma, where quarks and gluons, the stuff that protons and neutrons are made out of, are in a kind of free state. In the early universe, they were in a free state. And so that's the goal. That's what we're after with the particle accelerator that I work with that's near here. To give an analogy for what it is we're looking for at the particle accelerator, I always say that I have this tale of two snowballs. And so you imagine that we live on an ice planet. And some scientist says, guess what? I think there's this stuff called liquid water. And all the people would say, show it to us. And the scientists could say, I can't. It's the ice. It's frozen. We have to melt the ice to see the liquid water. And people would say, well, why should we believe it's there? And scientists would say, well, I have a plan. We'll take one of you go over there, and I'll stay over here, and I'll pick up a chunk of ice, and you pick up a chunk of ice, and we'll chuck our chunks of ice at each other. And when the two chunks of ice hit, maybe we can throw them hard enough so that the ice chunks will melt, right? And we'll see what's inside. And then the people would say, oh, that's great, let's do it. And he'd say, well, not so fast. You see, because we're not going to be, it's so cold on this planet that our water is going to refreeze instantly. So what we've got to do is take the refrozen shards of ice and from their properties infer that we had briefly made liquid water. And that's exactly what we do with the particle accelerator for a very, very brief instant in time, too brief to actually look. We make this, what we call quark-gluon plasma, and then it refreezes into the stuff that we're all made out of. And so we have to infer from the properties of these particles, from the way they're moving, and what kinds of particles we made, that we actually made this primordial soup in the accelerator. Right? So that's the game that we play in that field. So we do this with the relativistic heavy ion collider. And if you look at a satellite view of Long Island, which is not so far from here, 3.5-hour drive, you see this little circle? That's the only real human-made thing you can see in this satellite picture of Long Island. That's the relativistic heavy ion collider. It's a satellite view of the free space. And so that's where I work. I work at that collider there. And you can zoom in on it. And that's a helicopter sort of view of the collider. And you see the collider complexes are very interesting. They are usually made out of rings. You start to accelerate particles up to close to the speed of light in a little ring, and then when you get as fast as you can go in the little ring, you inject it into a bigger ring, and you get closer to the speed of light, then you inject it into a bigger ring, and you go even closer. So these days, the highest energy accelerators are actually chains of accelerators, like they are here. And so what we do is we inject particles at close to the speed of light into the relativistic heavy ion collider, RIC, and we make one beam go in one direction, and we make the other beam go in the other direction. And we organize the beam into these little bunches. There's about 110 bunches. And so we counter-rotate these 110 bunches. And then thousands of times per second, or millions of times per second, we cross the bunches. And we hope to get one collision in each crossed bunch. Just like the two people throwing the ice balls at each other. Every time these two bunches cross, we're trying to get at least one collision. And then some of those collisions, most of those collisions, if they're head-on enough, we try to make quark-gluon plasma. So that's the game that we play. And there are several collaborations. Actually, it's really interesting. There were 4 collaborations of the team that did this research. There are 2 really large ones. One is called Phoenix, and they have a big building here. And one is called Star, and they have a big building here. And the reason why they have 2 independent collaborations at the collider trying to discover this quark-gluon plasma is that if one group discovers it, the other group should see it as well, but the analysis done to discover it is completely independent. So you have some repeatability. You can prove that your experiment is repeatable by having multiple collaborations at the same location. And that's a major reason why at major colliders you usually have multiple research groups that work independently of each other. There's friendly competition, sometimes not so friendly competition between the groups. And they typically consist, in my field it's actually small, it's 500, 600 or so physicists and engineers, but you probably know that at the Large Hadron Collider, for example, there are thousands of physicists that work. And actually at the Large Hadron Collider, the LHC, they do exactly this kind of physics that I've been describing to you, where they study this quark-gluon plasma stuff. The atoms that we collide at this collider, the heaviest ones that we use are gold. So we'll take 2 fully ionized gold atoms, smash them together close to the speed of light, and see what comes out. So the detector that we use for this physics looks like this. So this is all, as of about a year ago, been torn apart because we're building a new one that's smaller and better. But this one, for scale, this is the size of a person there. You see that person on the right up there? So it's several stories high, the detector, right? And it's got some magnets here, and it's got thousands and thousands of channels to detect where these particles go. And you sort of take a picture of the collision, right? Millions of times per second. Well, yeah, millions of times per second. So the discovery, actually, of the quark-gluon plasma was successfully completed a fairly long time ago. In 2005, we claimed victory. We claimed that we had discovered this primordial fluid because all the research collaborations saw stuff we didn't expect to see, stuff that's consistent with the existence of this primordial soup, and so we declared that we had found it, and then it became, according to the American Institute of Physics, the 2005 story of the year. You might say, well, then you're done, right? You discovered it. But then we want to study its properties because it can teach us about the fundamental theories of nuclear matter. Quantum chromodynamics is the name of that theory. We learn more about it by studying this stuff. Okay. So I've done this research for about a decade. I've studied this stuff. And every summer, part of my research plan is to bring some number of Muhlenberg students out to Brookhaven National Laboratory in Long Island, and we help build detectors, or we do computer analysis of these huge data sets that we collect. And so this is a picture. Every year for a while, we would take a picture until the police kick us off of the Brookhaven National Laboratory sign, and there are also some bees, so it's not that much fun there. But I'd say about 1/3 of these students are Muhlenberg students, and there I'm a little bit younger there. And so we spend 8 weeks at Brookhaven National Laboratory. They get a stipend, and if they do 2 summers with me, typically they get to be authors on Phoenix publications. So a Phoenix publication usually has hundreds of authors because there's hundreds of collaborators, and anybody that helps with the collection of the data, takes data-taking shifts, and does some significant work for the collaboration will be a partner in publications that use those data. So the students don't actually understand the physics in those papers, but they did acquire the data, so they deserve recognition for that, and so they're listed as authors. Okay. So I've been doing that for about a decade. There's a couple students at Brookhaven this is one of the particle accelerator, the tubes that's inside the accelerator. The accelerator, you have to steer these charged particles, these ions in a circle, so you need magnets. And since you accelerate them to such high energies, you need really strong magnets. So the magnets that they use in the collider are superconducting magnets, because otherwise you couldn't get the particles to as high energy as we do. And and still keep them going in a circle without them going off straight-ish. Right? So these are 4 of my students from one of my years. One of them is, oh, 2 of them are in graduate school, one for astronomy and one for physics. Right now. This is a view of some of them working on building detectors. That's something that some years they spend a lot of time doing, but not every year. And that brings me to, I guess, something that's exciting for me in terms of talking to you, and that's that, you know, can we do high energy physics, that sort of fancy schmancy, cutting edge high energy physics, but we can actually do high energy physics here in the Lehigh Valley because nature has given us free of charge high energy particles that go through us every day as we age, probably help evolve us. And we can use the radiation that's around us to talk about the research, the sort of research that we do at Brookhaven National Laboratory, to recreate some of the detectors that we used in that giant experiment that I showed. And I'm hoping we can do interesting experiments together. So, how is it going to work? Well, the particles that nature gives us, sometimes I say God gives us, but I don't really mean God, of course, that nature gives us are these things called muons. And a muon is really a very massive electron. If you imagine an electron that's 200 times the mass of an actual electron, that's pretty much what a muon is. And so these muons are created because in the upper atmosphere, usually about 15 kilometers above the surface of the Earth, you have these amazingly high energy particles, much higher than anything you can make at RHIC, much higher energy than anything you can make at the Large Hadron Collider. You have amazingly large high energy particles that hit the atmosphere. And when these particles, usually protons, hit our upper atmosphere, they create showers of new particles created from the vacuum that come showering down on the Earth every day, right? And so there's a flux of them all the time. I can play the flux for you because I have a muon detector right here in this little cylinder. And so if I put the sound on, this thing's blinking from muons going through it mostly. And that's the rate at which muons are going through us, each of us, all the time. And these muons are formed from these high energy protons hitting the upper atmosphere and creating these showers. Sometimes, of course, you get extremely high energy protons. They think these might be coming from supernovas in other parts of the galaxy and other galaxies. And so these high energy muon protons, mostly that hit us, are called cosmic rays. And so we have these cosmic rays which hit the upper atmosphere. They create showers of elementary particles. And among those elementary particles is the muon, which I just played for you that was going through that machine. So that machine, what, about 10 of those would be a person? So about 10 times that rate is the rate that humans get. And how do we evolve? Through random mutation. And what's capable of creating random mutation? An ionizing particle. What is an ionizing particle? Well, a muon's an ionizing particle. So muons have played some role in the evolution that's taken place on this planet. So it's taken place some role in human evolution. So that's just one of the sort of important ways in which muons have affected us deeply. Yeah?
So the muons are high energy particles, what you're saying?
They are. They're ionizing radiation.
And they're moving faster than the speed of light?
They move close to, very close to the speed of light.
So in a sense, why couldn't you put one of those collectors out of space and have muons going into those things out of space?
Well, you could. It's a little hard. And we have built experiments in outer space. In fact, there are some fundamental questions that are best answered by placing detectors like that one in outer space, and that has been done. But the muons that I'm talking about actually aren't made in outer space. It's the protons that are coming to us from these supernovas and stuff in outer space. They hit our upper atmosphere and interact with atoms in our atmosphere. And that interaction creates a shower of particles which come to the Earth. And in that shower of particles, we have the muons. So most of the cosmic rays are actually not muons, they're protons, usually. And those protons create showers which have muons in them. But there's actually a deep observation to be made here, because you make these muons way up in the upper atmosphere, and even though they go the speed of light, they decay typically after about 2 millionths of a second. So if you do a little calculation, I think I did a little calculation. So this is my little cartoon right? You have a primary cosmic ray, like a proton. It hits the upper atmosphere, which isn't a line, of course. And you create this shower of particles. And in the shower of particles, this red thing is supposed to be a muon. That red one, now my pointer isn't working. There's a muon, and that muon, many of those muons make it down to Earth, right? I'm just pointing toward you here. Okay. Yeah?
How about the magnetic field of the Earth? How much does that affect the amount of
so actually, the
proton
magnetic
or
field,
cosmic rays that come in?
yeah, it plays an important role. The cosmic rays are affected by the solar wind too, because the solar wind affects the whole solar system, and so that has a big effect. But also the Earth's magnetic field has an effect on the trajectory of the muons. In effect, the Earth is kind of like a selector for the kind of muon you've got, because muons come in positive and negative varieties. You have positive, and that's right, so they bend in opposite directions. And so you can actually see a slight asymmetry in the number of negative muons and the negative positive muons, which reflects in the charge asymmetry in the particles that are hitting the upper atmosphere, because we have a proton, which is positively charged, we have a neutron, which is neutral, but we don't have many antiprotons, which would be negatively charged protons. And that can be reflected in the rates we measure at the surface of the
And
Earth.
that shields us too from those, right? I mean, there would be a lot more coming in?
No. These are like really high energy things.
Okay.
So when you read in the news about all these experiments they put deep underground, the reason they're putting those experiments deep underground is to shield the experiments from these things, because of all the elementary particles, the muon is about the most penetrating one got. So it doesn't really stop them from coming. They're like a bulldozer plowing through cotton candy. And so they don't get stopped so easily. They do decay though. And they do interact, and as they interact, they do slow down. And that affects them too in a way I'll tell you in a minute. Yeah?
So they changed the name from tachyon to muon? Is that where?
No, tachyons are a different particle, a different hypothesized particle. So a muon, they used to call them, very confusingly to a particle physicist, they used to call them mu mesons, which is a horrible name because a meson is something else entirely. But they actually happen to be close in mass to another particle, and so there was confusion in the early days about what they were detecting, and so they had these things called mesons, and they thought this thing was some kind of meson, but it wasn't. It was more like an electron, like I was telling you before, just a heavy electron. And so it never should have been called a mu meson. It should always have just been called a muon, which is like an electron. There's one other elementary particle, just like it, called a tau, which is even more massive than a mu. So we have this family of three particles that are like electron, fatter electron, right? Those are what we have. They're very penetrating, partially because they don't undergo nuclear interactions. They only go electromagnetic interactions. And they make it to the surface of the Earth and even into the Earth. They penetrate the Earth very quickly. Would someone else have their hand up? Okay. So these muons, they make it to the surface of the Earth, but if you assume the muon is going as fast as a muon can go, which is the speed of light, that's as fast as a muon can go. You can't go faster than that. Tachyon could, maybe, if they existed, but a muon couldn't. And nothing that we've ever discovered can, but that has mass. So the muons make it to the surface of the Earth. And if you calculate how far they should make it, given their lifetime of about 2 microseconds, I did a little back-of-the-envelope calculation here, 3 times 10 to the 8 meters per second for the speed of light, 2.2 microseconds for the lifetime of the muon, and you get a few hundred meters. Those muons should all be gone. There shouldn't be. What we hear here, that should not be happening. The muons should have all decayed into electrons, and those electrons should have all interacted with other particles, and we shouldn't be hearing this right now. What's going on? Well, it turns out that about the most coolest thing you can imagine is going on. What's going on is that Einstein was right, that different clocks move at different rates, right? If you're on a spaceship that's going close to the speed of light, your clock will run at a different rate relative to our clocks. And it so happens that the muon's clocks are running slow. So the muon doesn't know it's time to decay. To anthropomorphize the whole thing, right? The muon's clock has not gone through as much time. And so the muons are still there, right? Because they last on average 2.2 microseconds, but it's a probabilistic thing. They can last longer or shorter. But we shouldn't be receiving anything like this. The only thing we see it is because it's direct evidence of time dilation. It's direct evidence that time moves at different rates for observers, for objects that are moving differently. And so we get this big flux of muons in the Earth, and it's one of the first clear indications that Einstein was right, that time does not move the same for all observers. Time is different for different observers, and in particular, time is different for these muons. You can correct for it, and then we get the right rate at the surface of the Earth. That's an amazing thing, right? Just because we hear those clicks. How am I doing on time?
You're good.
How much?
Like 15 minutes.
15 minutes. All right, so this theory of relativity ties into this. I think that's really cool. So what can we do together? So we could build these muon detectors, you and I, and we could put them into the high schools, right? Because they're very easy to build. So this get up here, you could buy this from TeachSpin. I don't know if you ever used the group TeachSpin, but they built experiments, and this one's overpriced at about $5,000 or something. And that's too much for us. But here's a muon detector as well. And you can build this muon detector for about $100. And now we're talking about maybe something we can all get around. So we can build one of these little detectors. Has anyone seen it little flash? Maybe my computer's not powering anymore. Is it still flash? Okay, it flashes. Okay, so it's still powering. So this is a muon detector as well. It's less than $100. And we could put these in our classrooms in Lehigh Valley, say. And it would be very interesting because usually those go off like little lightning bugs, right? Different times, just randomly. But every once in a while, when there's a big shower, like some giant proton hits the upper atmosphere, in all our schools, they'll all go off at the same instant because there will be a huge shower of particles coming down from a big event. And that's actually a kind of exciting thing, because something I maybe didn't stress enough is that these primary cosmic rays are of great interest to physicists, because some of these cosmic rays are the highest energy things that have ever been measured. You can take, there's 10 to the 24 particles in a golf ball or something like that. And you can take one of these primary cosmic rays, and that one atom has the same kinetic energy as 10 to the 24 atoms in a golf ball. And these are huge, huge energies. The highest energies we've measured as particles are in some of these cosmic rays. And when one of those big ones, maybe not quite that big, but a fairly big one, hits the upper atmosphere, all of our detectors would go off at the same time. And we get to have detected that event because we could look at the timestamp on all of our little detectors and see that they all went off at the same time. And then, wow, we just discovered a big cosmic primary ray hit. So that's pretty cool. And it's pretty approachable as an experiment that we could all share. So there are other things, though, that you can do as well. Oh, here's, I guess, in the background of the cosmic ray detectors. These are all developed, by the way, at MIT. And there's a guy there that was working on a neutrino experiment, and he needed to build little low-cost detectors to test the bigger detectors in the neutrino experiment at the South Pole. And the little detectors looked so useful, he said, wow, we can use these for outreach. And so he kept working on his design, and he's worked with some other groups. And now there are high school students in Boston and other places that are building these as a matter of course. And now you can do high-energy physics in the classroom. Right? And as I said, they're not very expensive at all. And so on the left there, you see what is sort of an artist's rendition of a cosmic ray shower with the muons and other stuff. But something else you can do with these things, if you imagine I have two of them, let's say I have two of these guys, and I put them in a tube or something, so I have one here and one here, what have I now built for myself?
It's up.
You can look for them both, the two of these going off at the same time, and then you know the direction that your muon is going in. Right? If it went through this one and it went through this one at the same moment, its trajectory was straight down. If I put the two like this, and it goes through this one, and it goes through this one, you can't come over there. Right? And so now you have a muon telescope. Right? They've thought of using muons. In fact, they've tried to use muons, I think successfully, to find hidden rooms in pyramids. Because muons are very penetrating, but the flux will change slightly if you're going through air or you're going through material. So if you go to a pyramid and you think there's an empty room, you put a muon detector on the other side of that room, and you see the flux changes significantly, you say, oh, that room must be empty. I'm getting more muons when I look in this direction. I bet there's a chamber there. So they've tried to use them for that purpose. There's been proposals to use them for homeland security as well, because you could look into metal containers that no other particles can go through, muons can go through almost anything. So you can have steel containers, and you can do a same thing, kind of an X-ray thing, to see if the container is empty, or maybe it has a big slug of plutonium in it, or God knows what, right? So anyway, you take two of these detectors and you place them next to each other, and you use coincidences between the two to look at the rate of muons in different directions. And actually, that's a well-known measurement that was cutting-edge physics in the 1950s or something. So there's a plot you can make. Here's the plot you can make. So this is the number of muons by looking at different directions in the sky by using two detectors and coincidences between the two detectors. So you just move the detectors like this. And you see that this would be looking straight up, at 0 degrees would be straight up. And then you can move towards 90 degrees and look at this beautiful shape that gets drawn out. And actually, this line is a cosine squared theta function. And so the dependence of the muons, the angular dependence of the muons, goes amazingly like an ordinary function that we use every day squared. It goes like cosine squared of theta. Why does it do that, right? So why do you get this distribution? So I had some summer students this summer who created a computer simulation that included the physics of decay and the physics of energy loss of the muons, and can replicate this curve as a Python computing exercise. But it's a beautiful curve, and the data fit it really well. And one thing that's kind of interesting about it is you notice there's sort of a systematic dip on the right side and a systematically high on the left side. And that's because the building in which this detector was, if you tilted it one way, you were going through the building. And if you tilted it the other way, you weren't going through the building. So actually, you can see the building in the data. And it's kind of cool. So I think there are all sorts of things we could do with these detectors. There's all sorts of physics we can do with these detectors. And I'm really hoping that some of you would like to deploy them in your classrooms, and you could teach about particle physics, you could teach about detectors. I didn't talk much about how these things work, but I could. And the students can even build them. It involves some soldering, and what's worse, actually the students would probably be much better at it than I am, because these things, this little one is built out of surface mount components. I don't know if surface mount components are teeny tiny components. When you solder them onto a printed circuit board, for me with my shaky hands, very difficult, but I have a feeling students would have no problem at all. Anyway, you can solder these things together. They're really just made out of a piece of plastic. The heart of these detectors is something called scintillator. You see this? It's just a square of plastic in this bag. And it looks like a square of clear plastic, which is what it is. But it's doped with material so that if you're in complete darkness and a charged particle goes through it, it makes a little flash of light. And so this is a detector. This is actually a very important detector. In the big one I showed at Brookhaven, there's lots of these kinds of things around in the Phoenix detector. And it's just a piece of glowy plastic. Right? Rutherford would have been happy to have it when he did the Rutherford experiment. And then what you do is you hook some kind of light sensor up to it. Like a photomultiplier tube is typically what's been done for the last century. But now we have new detectors, new solid-state detectors that are taking over. And so there's no way you're going to be able to see this, but in this box, I have a little printed circuit board with a teeny little, maybe I'll pass it around. It's got a teeny little rectangle in it. That's the new, that replaces the photomultiplier tube of the last century. So here and so you can build your detector by taking one of these little rectangular chips, which is really just an array of diodes, and plastering it against the scintillator. And then if you build your circuit correctly, your electronic circuit correctly, every time the little plastic gets a flash of light in darkness, it will affect this little rectangular chip, which will create an electronic signal, and that's what's causing the counting you're seeing on that little detector there. It's actually using exactly this little kind of chip. So I'll pass it here, you can look around. But don't hurt it, that's an actual model that I'm testing. Be gentle with it.
We don't hurt. We don't like that. Only our students do not.
So I guess that, is it good on time?
We have 5 minutes.
5 minutes. So should I take questions now?
Or tell them about the little orange thing that you had me carry.
Yeah. So, so it turns out that the radiation dose that we get, that helps with evolution and everything, that's only a portion of our total radiation dose. And one thing that always amuses me is that how negligent we were in the early days regarding things that were radioactive. So this is just a piece of Fiestaware, right? And it's real Fiestaware from, I don't know, a few decades ago. But it's highly radioactive, so I have a little Geiger counter thing here. Not so highly radioactive, you have to worry if you hear it.
That's how you keep your breathing on.
Oh, it's going crazy. So that's this Geiger counter, and if I move to here, it's probably normal. Nothing, right? If I go back to sometimes I'll start a class in the beginning when I'm teaching about the atom bomb or something, and I'm teaching about radioactivity, and I'll say, oh, does anyone want some gravy or water, whatever his name is, So yeah, there's a lot of, in addition to the cosmic ray experiments, there's a lot of basic radiation experiments that you can do. Study, the sort of standard stuff. I don't know if you folks do this in your classes, if you teach about alpha particles, beta particles, and gamma particles, and basic kinds of radiation and things like that. You can do all of that sort of thing with these detectors as well. I think that's probably good. I have a few pieces of simulator. This is from a prototype at Brookhaven National Laboratory, where it's using solid-state detectors like in that box. But they want to get a uniform response. So what they do is they put a fiber optic cable in the simulator. Can you see that it's glowy, a little green glow? That's because there's a fiber optic cable here. And then if you get a flash of light anywhere on this block, it kind of gets trapped by the fiber optic cable. And the fiber optic cable points right toward the little electronic detector that's in that box. And then you get your signal. So they have thousands of these in one detector at the lab. And so we don't have thousands, but 2 is good, right?